This will be the line. I forgot to record. Okay.
Hocam, when you will share the recordings with us?
Excuse me?
When you will share the recordings with us? Because last time you recorded but haven't sent the recording of the Monday.
You're right. After this lecture, I will share the videos.
Okay, thanks.
L2 will be written as follows. X is minus 2s plus 4. Y is s minus 3. All right. We want to find the intersection. So you know how to find the intersection. To find L1 intersection L2, we equate these equations. So we need to solve. X is equal to minus t plus 2 in the first line. For the intersection, it must be the same as what is x for the next one. So t minus 1 equals s minus 3 minus t plus 1 equals 3s plus 3. So this means that at this intersection point, it will occur when at t and s, when they satisfy these two equations. Okay, so let's consider. Let's now write this thing more explicitly. So let me keep it like that. And then, so let's take unknowns on one side, constants on the other side. So I will have 2s minus 2 on the left and 2 on the right. 4 minus 2s plus 4. Yeah, there is something wrong in the book, I think. Oh, okay. So 2s minus t is equal to 1. T minus...
Hocam, it should be 2.
It should
2s
be
minus
2.
t is...
Yeah. T minus s equals minus 2. And minus t minus 3s is equal to 2. Okay. All
Hocam, en
right.
yukarıdakinden bahsediyorum. 1 yerine 2 olması gerekmiyor mu?
Where?
2s eksi t.
Here?
2s minus t is 2, right? But you wrote 1.
2s minus t should be equal to 4.
Okay.
Yeah. T minus s must be equal to minus 2. Minus t minus 3s must be equal to 2. Okay. And then from here, so we get okay, we get from here, what do we get? So we need to solve these two things. So if we add, so from these two, So let's add these two things. We get minus s minus 3s, so minus 4s equals 0. So from here we get s is equal to 0. If s is equal to 0, then t is equal to minus 2. Okay, so let's also check if this satisfies the first equation. Yes, so when s is equal to 0 and t is equal to minus 2, this is satisfied. So first equation. So you see, we got these two numbers, values, from the last two equations. But we should also check what happens with the first equation, right? So when we put s equals 0 and t equals minus 2, the first equation is also satisfied. Satisfied. So really that s equals 0, t equals minus 2 is the only solution of this system. So s equals 0, t equals minus 2 is the only solution of this system. Thus, what is the intersection point? These two lines will intersect at a single point. And this intersection point will be, let's denote it by P. So it will be what we get when we put s equals 0. So let's put s equals 0 in the second equation. We get 4 minus 3. So this is our intersection point. The intersection point is E4 minus 3, 3. Okay.
Hocam, can I ask a question?
Evet.
Hocam, how we find that intersection solution, because as is 0, but we replace them in equation.
We find s is equal to 0 and t is equal to minus 2.
Yes.
Is this correct?
Yes.
Okay, so
Then we replace equation.
we put these values into the equation of the line to find the point. Yes. So when s is equal to 0 or t is equivalently t is equal to minus 2, the intersection occurs. So I put s equals 0 in the second line. The equation of the second line is given by s. You see?
Yes.
So when s is equal to 0, so I put s equals 0 in here. So I get 4 minus 3, 3. So this will be my, then this would be the point which is on L2, also on L1. So it will be the intersection point. If you like, however, if you put t equals minus 2 in here, you will get the same point. So let's put t equals minus 2. So we will get minus 2 plus 2, again 4, minus 3, and 3. We get the same point. So to find the intersection, we need to put these numbers into the equation and get the point, because intersection is a point. These are values for the parameter. So the intersection point occurs when these parameters have these values.
Every time intersection has to be a point.
The intersection has to be?
Point.
Yeah. It has to be XYZ, yes. The intersection point has to be XYZ. XYZ given in the equation, XYZ given depending on this parameter t. So this is X, this is Y, this is Z. All right, let's take one more from the book, the example. So this time let's take 555. So again, say find L1 intersection L2 if L1 is given as follows. Book's notation, but this is not a standard notation, I must say. 2t plus 1, t plus 2, and 2t minus 1. And the second line is given as 3s plus 2, s plus 3, 2s plus 2. Okay, again, this notation means L1 is the set of points P whose position vectors have components given by these formulas depending on T, and the other one is given depending on S. Again, in our parametric notations, how do we write these things? X will be 2t plus 1, y will be t plus 2, z will be 2t minus 1, and L2 will be like x 3s plus 2, s plus 3, and s plus 2. Again, we want to find the intersection. So we need to solve these two at the same time, meaning that x here will be same as x here. 2t plus 1, same as 3s plus 2. t plus 2, same as s plus 3. 2t minus 1, same as 2s plus 2. Well, the difficult thing is to solve this system. Again, as we did in the previous example, let's collect unknowns on one side. Two t minus 3s will be 1, and then t minus s will be equal to 1, and 2t minus 2s will be equal to 2 plus 1, which is 3. Okay, how do we solve these things? Well, we do it as we did before. So we have two unknowns, 3 equations, but we know how to solve for two unknowns, 3 equations. For example, let's subtract from the first and third. We can get the following. So subtracting, let's subtract first one from the second one, if you like. From first one and third one. So subtracting or let's subtract the first one from the second one. Subtracting first from third. What do we get? So I will get minus 2t, so this will disappear. And then I'm going to have 3s minus 2s. I'm going to have s. And then minus 1 plus 3. Okay, so you see, from the first and third equation, using that, I got s equals 2. So if s is equal to 2, what is t? So if S is equal to 2, so I'm going to have minus 6, 1 plus 6, 7. T will be 7 over 2. If I'm not mistaken, from the first equation. From the first. All right. Okay, but now we have not used this second equation. Let's now check if these values also satisfy this one. Now put into the second equation. T is 7 over 2 minus S is 2. Second equation would be this one, but this will not be true. Not true. So not true. Oh, you see, this system, what does this mean? This means that this system has no solution. What this says, so this system has no solution. Too many equations. Okay, so this says that for our lines, they cannot intersect. L1 intersection L2 is empty. They do not intersect. Not intersect. All right. Okay, let's draw the pictures of this one. We know that if two lines, if they do not intersect, they are either parallel or they are skew, right? So skew is like that, you know. Skew. But it is also possible that they are parallel. So which one? Well, are these two lines parallel? So how do we check if two lines are parallel? Remember, we look at their direction vectors. Right? Two lines are parallel if and only if their direction vectors are parallel. Let's look at the direction vector. What is the direction vector? What is a direction vector for L1? Remember, we write the direction vector looking at the numbers in front of the parameter. A direction vector for the first one will be this one, 2, 1, 2. Direction vector for L2 will be 3, 1, 2. Okay. These are the direction vectors. Fine. Are these parallel now? Are these direction vectors parallel? No, because they are not multiples of each other. Not parallel. Not parallel. So we are in this picture. These two lines are skew lines. Because, again, they are not intersecting as we saw looking at this system. And they are not parallel as we saw looking at the direction vector. Any questions here? Okay, this is how we deal with intersection questions. We write a system combining the parametric equations and try to solve this system. If we can solve it, fine, we get the intersection point. If we cannot solve, then they will be skew lines or parallel lines. Then we decide by looking at the direction vectors. This procedure is always the same. Okay, let's now discuss regarding lines in space, the angle between finding the angle will be acute angle most of the time between lines. Okay, so the picture is as follows. We have two lines, intersecting lines, between intersecting lines. So you see there are two angles. There is this one angle between these two lines, which will be acute angle. So it will be less than 1/2, pi/2. Okay, so we want to find this angle alpha. Most all right. So for this we use the direction vector. So to find when we hear the angle, the term angle, we should remember angle between vectors. How we find. So let's say that we have two lines, L1 and L2. B lines intersecting. And alpha be the acute angle. Between them. Meaning that alpha is between 0 and pi/2. So you see there is also another angle between, there is also this angle, which will be, according to this picture, greater than pi/2, but it will be the obtuse angle. So we are interested in the acute angle. Between two lines, there is acute angle and also obtuse angle. We want to write a formula for the acute angle. Okay, how do we find this? As I said, for this we use direction vectors. So let u1 and u2 be direction vectors. Vectors of these lines, of L1 and L2. So it will be what? It will be, for example, like this. U1 will be parallel to this one, and U2 will be parallel to this one, U2, parallel to L2. Okay, these two vectors, there will also be an angle between these vectors. So let theta be the angle between U1 and U2. So let me draw a picture here. This will be U1, this will be U2. For example, theta is the angle. Fine. What is the relation between theta and alpha? Then the relation between theta and alpha will be the following. So alpha will be either equal to theta or p minus theta. Alpha equals theta, or alpha equals pi minus theta. Why this is so? Because of the following. If our picture is like that, this is L1, this is L2, and U1 and U2 are like that, then in this picture you see alpha and theta are the same. Alpha equals theta. However, you know that direction vectors are not unique. This is L1. This is L2. We can have a direction vector here, U1. And the second direction, the direction vector of U2 might very well have been in this direction. Then in this picture, if we have such a picture, then alpha will be equal to pi minus theta. Anyways, in any case, we have the following. So if we look at the cosine of these angles, cosine of alpha will be plus or minus cosine theta. Well, why am I looking at the cosine? Because I can compute cosine of the angle between two vectors using dot product. So let's write this cosine theta. Cosine theta is, as you know, u1 dot u2 divided by length u1 times length u2. Okay. If we like, we can write this as so cosine alpha. Since alpha is angle between 0 and pi over 2, its cosine will be positive. And it will be equal to the absolute value of this ratio. This is the picture. To find the angle between two lines. Let's take an example. Find the cosine of the angle. Find the angle between the lines L1 given as follows: x, y, z equals minus t plus 2, t minus 1, minus t plus 1. L2, again, x, y, z, minus 2t plus 4, and t minus 3, and 3t plus 3. Okay. All right. Let's find the angle. Well, first of all, for this, we need to check if they intersect. L1 and L2 intersect. Because these are same lines as our first example. Our first example today that we did. So we can speak of the angle between them. Okay, let's now write the direction vectors. Direction vectors. Direction vectors. Which I will get looking at this parametric equations. You know, I take the numbers in front of the parameter. Direction vector x component will be minus 1, 1, minus 1. Direction vector for this will be minus 2, 1, 3. Okay. Fine. Let's now compute our formula. Cosine alpha will be u1 dot u2 divided by length u1 times length u2. Let's compute these numbers. u1 dot u2 minus 1 times minus 2 plus 1 times 1 plus minus 1 times 3 divided by length u. I also have absolute value in here. Divided by length of u minus 1 squared plus 1 squared plus minus 1 squared times length u minus 2 squared plus 1 squared plus 3 squared. Well, we see that numerator is 0. So the ratio is 0, meaning that cosine alpha is 0, which means the angle is right angle, 90 degrees. So the picture for these lines should be then like that. These are perpendicular lines, perpendicular. Okay. Now, after we seeing how we write equations for lines in space, so you see we have something new. So we had this notion of vector equation and parametric equations, and we did this for lines in space. Now one may ask if, well, we also have lines in plane, right? So can we do the same things in the plane? Yes, absolutely yes. So let's now see how we do this. So let's discuss now vector equations for lines in the plane. This would be section 3.4 in the book. So section 3.4 in the book. Well, L. Let's say this is our line L. Again, let's say that as we did in the space, let's say that this line passes through P1 in the direction of a direction vector u. All right. And let's write an equation for this one, vector equation. You remember how we write vector equations. Vector equation is something which tells us when a typical point P with typical coordinates x, y, z is on L. And if you remember, we did this as follows. P1 is already on L. If P is another point, then we have this, we can consider this vector P1P, and it should be parallel to U, and the parallel means multiple. So it will be a multiple of U. So this would be our vector equation. But we can write it in slightly different forms. For example, we can write this vector P1P as, you know, P minus P1 equals T times U. From here, we can write as P1 plus T times U. This would be our vector equation. For L. This is also a vector equation, doesn't matter. This is same as what we did for lines in space. However, there is one, what is different? The difference is all the following. So we have also other type of equations for lines in the plane. So this line L also has a linear, or also called normal equation. So remember, this line also has an equation like that. This is still there. We also have a vector equation. However, for lines in space, we do not have an equation like that, as I said before. We will see why next time. So for lines in space, we only have vector equation, not such a linear equation we have. Let's now take an example. Find a vector equation. Also, there is not only one vector equation. There are many, depending on your point P1 and direction vector. But they will all describe the same equation. Find a vector equation for the line x minus y equals 1 in the plane. We are in this xy Cartesian system now, and let's sketch the graph of this line. Line is like that. X minus y equals 1. All right, so this is 1. This is minus 1. Fine. Let's now write the equation. To write the equation, the vector equation, you see we need two things. We need a point on the line, and we need a direction vector. Well, for this one, let's take 2 points. So, note. For example, these intercepts. Let's call this one P1, let's call this one P2. P1, 0, minus 1, and P2, 1, 0, are on this line L. And in fact, they are intercepts. Anyways, doesn't matter. Well, now we need direction vector, you know, and we can write a direction vector using these 2 points. The vector P1, P2 is a direction vector. Direction. Let's write the components of this direction vector. What is P1, P2? It will be P2 minus P1. So it will be P2 minus P1. So 1 minus 0. 0 minus 1. So 1, 1. This is the direction vector, 1, 1. So 1, 1 is like that, right? Direction vector. 45-degree angle. Okay, so we know a point. In fact, we know many points on the line and direction vector. Let's write the equation then. Our vector equation will be, so I write this one. So P, what is P? P is typical point. It will be P1 plus T times U2. T times U. Let's write the components if you like. So P1 is 0 minus 1 plus T times U. U is 1, 1. Okay. Then if we write it explicitly. So we will have t as the first component. Next component will be minus 1 plus t. Yes, so you see, we can describe points on this line by this notation, where t is parameter here again. So t is parameter. So this is the vector equation. Again, we can write parametric equations. So x will be equal to t, y will be equal to minus 1 plus t. So parametric equation. But there will be no z. So the point is, again, we can do the same things for lines in the plane. Okay. Well, similarly, we can describe vector equations for half lines. After discussing vector equations for lines, let's now discuss vector equations for half lines. Half lines. All right. So let's take the following type of a picture. Let's say we have a point P1 in here. All right. Okay. And we have half line. So this could be in the space or in the plane, doesn't matter. Let's say we consider this half line, the one starting from P1. How can I write an equation for this half line? For this, I'm going to use a direction vector. Again, let's say that my direction vector is like that. Then how can I describe a typical point P in here? Let's describe. Well, so P is, when is it going to be on this half line? Half line, starting from P1 in the direction of the vector u, if and only if. Well, again, we can consider this vector. So our basic idea in studying lines and questions about lines is to use vectors. So I should consider this vector P1, P. Well, this will be parallel to u, this direction vector u, however, in a special way. So this is half line. So normally, in such a picture, this P1, P will be in the same direction as u. So it will be t times u. However, t should be greater than or equal to 0. So half line, we should describe it this way. So we should not allow t to have negative values, because if t takes negative value, so you know, for example, if we take t equals minus 1, then we should consider minus u in the other direction, but the other direction we do not want to consider. So to describe this half line, we should consider this vector equation. So this is the same vector equation for the whole line. However, we restrict the domain of the parameter. So we take not all values, possible values for t, but only for positive values. Then this would be the equation for the half line. Or if you like, we can write this as P1 plus T times 0. This is the half line for this picture. U is showing the direction of the half line. Oh, this is same. So same for lines in space, and in the plane. Okay, so this is All right. Okay, so I think we had enough, so we can stop here for today. Next time we will continue on Monday. All right. See you next time.
Hocam,
Evet, sorunuz varsa alabiliriz.
hocam ben tamamlamadım da son soruyu.
Efendim?
Son soruyu tamamlamadım da.
Sonda soru sormadın mı? Hangi soru?
Ha,
Yukarıdaki mi soruyu mu?
evet.
Şunu mu? Bunu mu?
Evet hocam.
Evet, ne?
Orada X ve Y doğrularında ki noktaları bulduk.
Evet, 2 nokta buldum.
Ondan sonra neden direction vektörü onların arasındaki farka eşitledik?
Çünkü aralarındaki fark bir vektör oluşturuyor değil mi? Görüyorsun.
Evet. Evet oluşturuyor.
P1, P2 neresi? Şurası.
Evet.
Evet, bu oluşan vektörün özelliği ne olacak?
Yani
Oluşan vektör doğruya paralel olacak.
evet.
Dolayısıyla biz doğruya paralel bir vektöre ne diyoruz? Direction vektör diyoruz.
Anladım. Üzerinden bir vektör seçiyoruz ama onu paralel olarak da öteleyerek yapabiliriz değil mi?
Tabii öteleyebiliriz. Çünkü vektörü ötelediğimiz vakit vektör değişmiyor biliyorsun.
Evet.
U yazdığımla o P1, P2 gene aynı.
Anladım. Sadece üzerinden geçen noktalar değişiyor ama bu fark etmiyor sanırım.
Efendim? Son kısmı anlamadım.
Peki vektörün geçtiği noktalar değişiyor. Yani
Onun önemi yok. Biz vektörü hangi noktadan geçtiği için bakmıyoruz. Vektör bize sadece yön söylüyor. Yönde hangi noktada olursa olsun aynıdır. Kuzeydoğu diyor mesela bu şekilde. Kuzeydoğu mesela benim bulunduğum yerde de aynıdır, aynı yöndedir. 2 adım atsam ileride de aynı yöndedir. Vektörü sadece direction vermesi için kullanıyoruz. Nerede çizdiğimizin önemi yok.
anladım. Tamam. Ondan sonra da şey yaptık. Orada P dediğimiz şey tam olarak ne oluyor hocam?
P dediğimiz o doğru üzerindeki herhangi bir nokta. Tipik genel bir nokta P. Herhangi bir P noktası. Koordinatları x, y olan doğru üzerindeki herhangi bir P noktası.
Genel equation'ı bulmak için öyle bir nokta yazdık.
Evet. Çünkü genel equation demek genel bir noktayı bize söyleyen equation demek. Bu genel P noktası, x, y koordinatlı P noktasını bize ifade etmek istiyoruz. Vektörlerle ifade etmek istiyoruz. Bu P noktasının özelliği ne olacak? Bu P noktasının özelliği işte yukarıda da yazdığım gibi P1, P vektörüne bakarsan az önceki vektörün katı olacak. T çarpı U olacak yani. P1, P2. O zaman P'yi bu şekilde yazmış oluyoruz.
P2 ile de toplayabilir miydik peki?
Evet doğru. Onları da toplayabilirdin evet. O zaman başka bir denklem elde ederdin. Yani şu yazdığın alttaki kısmı diyorsun değil mi?
Evet alttaki kısım.
Şurada mı? Şurada P1 yerine P2 de yazabilirdin. Evet. O zaman başka bir denklem elde ederdim ama sorun değil. P ama buradaki P yani genel bir vektör dediğim gibi. P2 artı T çarpı U. Bu da bir vektör equation olurdu. Ama biraz daha farklı görünecek. Açık yazarsan T çarpı U yerine 1 yazacağım. O zaman ne olacak? 1 artı T Evet, 1 artı t olacak. Evet, o zaman denklemimiz bu şekilde olurdu. Az öncekinden biraz farklı olabilirdi ama gene aynı doğruyu anlatıyor bize.
Tamam, teşekkür ederim.
Rica ederim. Başka sorusu olan var mı? Tamam, o zaman bitirebiliriz. Bu videoları da en kısa zamanda ekleyeceğiz. Size mesaj göndeririz. Şimdi bitiriyoruz.